Dear all, welcome to our electronics laboratory. Today we are going to observe the IGBT characteristics of the IGBT installed here inside the 2701 kit. Yeah, this is manufactured by Scientech, and we'd like to thank EXS project for the support for us to purchase this equipment. And IGBT is an insulated gate bipolar junction transistor. So it has the properties like that of BJT, a transistor, and MOSFET. The gate is insulated, yeah, and we apply the gate voltage from here. This is collector, this is emitter, and we will observe the collector emitter voltage and collector emitter current as well. These are grounds, these are potentiometer. They will change the resistance, and hence the input current will be changed. For example, this P1 is the potentiometer 1. So if we change the resistance, then we are going to vary the gate current. Internally, the 15 volt voltage source has been connected to this pot, and hence while changing this pot position, we are going to vary the gate voltage. Similarly, this P2 resistance of 5 kilo ohm is connected in the collector emitter region. So if I am going to change the collector emitter voltage, then my collector emitter current will change, provided that the sufficient gate has been provided and it has not reached the saturation. So students, basically what we need to know today is that what is gate, what is collector, what is emitter. I'll be explaining about the role of gate in this video. We have the lab manuals associated with the Scientech 2701 kit. So we will go one by one through this kit. So this is the study characteristics of IGBT. We will understand the principle of IGBT and draw the output characteristics. This is a safety instruction, and I'll move to directly to the procedure as you have already studied theory in your classroom. Later on, I will be explaining about this graph. So while watching the video, please be careful to observe the parameters according to the x-axis parameters and y-axis parameters of this graph. On the y-axis, there is collector emitter voltage. So in our kit, this is collector and this is emitter. So we will be measuring the collector and emitter voltage. Emitter is connected to the ground, so we will be connecting the D and ground points to observe the collector and emitter voltage. Similarly, we can connect E and ground, F and ground. They are same points. Now along the D and E, we will connect one ammeter to observe the collector current, and we will observe the collector and emitter voltage by connecting F and ground to the voltmeter in order to observe the collector emitter voltage and collector current. So in this graph, there is a collector emitter voltage on x-axis and there is collector current on y-axis. The graph is dependent upon the gate voltage. As we go on increasing the gate voltage, then for the same amount of collector emitter voltage, we will be obtaining higher the values of current. This is because the more the gate, there will be the more number of charge carriers and more charge carriers can pass through the collector emitter junction, resulting the increment in collector current. We will observe this in the experiment. So here is the procedure on the next page. Yeah, I will go through it one by one and do the experiment. Now first I will be rotating the P1 in fully clockwise direction and P2 fully in anti-clockwise direction, so that P1 will be in maximum position and P2 will be in minimum position. Internally, the 15-volt source has been connected to this pot, and similarly the 35-volt supply has been internally connected to this pot P2. So now I am going to connect the emitter between the port D and E in order to observe the collector current. So between the D and E, I will configure this emitter in the milliampere region, and now I will connect these wires in the D and E region. Now this will give the reading of collector current in milliamps. Now I will connect the point A and B by this 2 mm patch cord cable in order to supply the gate voltage to the gate. Since the gate is insulated, we are only going to apply the electric field to the gate, and hence the charge carriers will be available in collector and emitter regions. So when I change the pot P1, the new values of voltage will be applied to the gate. Now I will connect the voltmeter between the point C and the ground in order to observe the gate voltage. I will configure it the voltage, then I will connect this wire in the C and the ground. This will measure my gate and emitter voltage. Now I will switch on the power supply and I will vary the potentiometer P1 in the counterclockwise direction to set the gate and emitter voltage between 5 volts around. So here you can see the gate emitter voltage is changing. I will set it over 5.5 volts, and now the gate region of the IGBT has been electrified. Now I will be connecting wires in the collector and emitter region or the ground. So if I change the potentiometer P2, I will be changing the collector emitter voltage as well. So now I put the collector emitter voltage around 2.88 volts, and I can see there is a current in the collector emitter region to be around 1.6 milliamps. Has there been no gate, then there will not have been a flow of current in the collector. As you can see, this is the gate and emitter voltage, this is collector and emitter voltage, and this is collector current. Now I have been applying the 5.5 volts to the gate, and also in the collector emitter region I have been applying 2.81 volts. So if I turn off the gate supply, then the current will be zero in the collector region, because simply this cannot operate with the application of the voltage if there is no gate. Now if we apply increasing the voltage between the collector and emitter junction without applying gate in the higher voltages, it might be a disaster, like this might be breakdown or something like that. Yeah. So when I increase the gate voltage, the more charge carriers will be available, and the current will increase in the collector region from 1.1 to 6 ampere. Now as I go on increasing the gate voltage, the current is constant, because the gate has saturated with this emitter voltage. So now I will go on increasing the collector emitter region voltage, and you can see the increase in collector current. After some point, the collector current becomes constant, and it is irrespective of the VCE voltage. So we will be obtaining the flat curve as we go on increasing VCE over the x-axis. The collector current is constant, you can see that. So we will be obtaining the flat part of the graph on the higher voltages of collector emitter junction. Now if I slightly change the gate voltage, then the collector current will increase. This means that we will be getting the upper positions of the graph as we go on increasing the gate voltage. So I am increasing the gate voltage. I increase to 8 volts, and you can see the collector current has increased. Now it is constant with the gate voltage. But if I change the collector emitter current or voltage, then there is change in collector current. Okay, this much for today. Thank you.